Hi, I'm Mrs. B. Welcome 4th and 5th grade. We are going to talk about science today. Our focus today is going to be on speed and energy. And before we get started, let's do a quick review of our senses to get them ready for our lesson today. So our 5 senses, we're going to use our sense of sight whenever we can, our sense of taste whenever we can, our sense of smell, our hearing, and our sense of touch. I want to show you a couple of objects here that I brought today. I brought a wiffle ball. So a wiffle ball is plastic and it has small holes cut out of it. It's hollow. It's not solid. Maybe you've used this before to play with. I also brought a tennis ball. It's made out of rubber. It feels heavier than the wiffle ball. I also brought this exercise ball. When you first look at this exercise ball, do you think it's heavy or light? It's actually very light. I also brought another exercise ball. And this one, I know how much it weighs. It weighs 8 pounds because it says that. It's pretty heavy. I also brought, make sure it doesn't roll away. I also brought a basketball. And the basketball is definitely lighter than this ball. And I'm going to have to compare to see which one's heavier between this exercise ball and the basketball. So today we're going to talk about speed and energy. And so what questions come to your mind about speed and energy and maybe some of the objects I brought with me today? Let's practice asking questions. What is a what question that you have about speed or energy or any of the items I brought? What is energy? We had a previous lesson, and we'll review energy in a minute, but what is energy? What if I test all of these different objects? Will they all have the same result when it comes to speed and energy? When? When will the lighter balls roll faster than the heavier ones? How? How is speed and energy related? Why is speed and energy related? So hopefully you checked out the lesson on energy, and it was an introduction to types of energy. And I want to do a quick review of types of energy that we can observe around us, and maybe some examples for each one. So energy is the ability to do work. What does that mean, ability to do work? Does that mean that I get in a car and I drive and I go teach at a school? Or does it mean that I'm going to go work at a post office? Work means that we are using a force, a push or a pull, to move an object or heat up an object. One of the types of energy we talked about last time was mechanical energy. And what was an example of mechanical energy? Mechanical. There we go. One type of mechanical energy is when we see the parts of a bike moving. The gears with the pedals. Using scissors is another example of mechanical energy. We also saw an example of light energy. And there are different types of light energy. Some we can see and some we can't see. And sunlight is a type of light energy, or when we use a flashlight to see with. We also talked about electrical energy. Electrical energy, we can see that when we use batteries or turn on a switch to turn a device on, to turn the lights on. We also talked about heat or thermal energy, and we use thermal energy when we use a stove to cook our food. Maybe you have an electric stove, maybe you have a gas stove. Do you remember what other type of energy we talked about last time? We also talked about sound energy, and that's when material vibrates and then those sound waves travel through the air and we can hear. We also talked about energy transfer. What were some examples of energy transfer? Energy transfer means that energy goes from one object to another or from one type to another. And that's something we're going to talk about today. So here are some examples of energy transfer. For example, a battery in a flashlight uses electricity so that we get light energy. Another example can be that a solar panel uses sunlight and converts it to electrical energy. One more example, we plug our TV into an outlet, and that runs electricity into our television, and then we get light and sound energy from our television. So these are types of energy. Energy also has forms. And so two forms we're going to talk about today are kinetic energy and potential energy. Kinetic energy is energy in motion. When we see objects moving, they can have kinetic energy. Potential energy is when energy is stored. And we're going to see some examples today and explore some examples of kinetic energy and potential energy. So in order for us to start to make sense around kinetic energy, I want us to look at the objects I brought today. And I'm going to put them in order from lightest to heaviest. And I'm going to use my sense of touch to feel and to see which is heavier and which is lighter. I predict that this is going to be the lightest one. So I'm going to compare this to the tennis ball. And I feel that this one is lighter. And just to make sure, I'm going to compare it to this because this is really light. This is definitely the lightest object I brought. The next lightest object, I think, is the tennis ball. But I want to double check and compare it against this exercise ball. Definitely, this tennis ball is the next lightest object. So I have my wiffle ball, my tennis ball. Next, this gray exercise ball is definitely lighter than this basketball. And then for sure, this 8-pound exercise ball is definitely the heaviest object I brought today. So here is the order of the objects I brought today, from lightest to heaviest. And when I talk about kinetic energy today, I want us to focus on mass. And I talked about mass in the last lesson when I talked about gravity. So let's do a quick review between the difference between mass and weight. Mass is anything that, how much there is of something, okay? So I have mass, you have mass, everything around us has mass, things in the universe have mass. So that's how much of something there is. When we have mass and we multiply it by gravity, we get weight. So our mass is the same on Earth, on the moon, on Mars. But gravity on Earth, moon, and Mars is different. And we would have a different weight because weight is the force of gravity. We would weigh different on the Earth compared to the moon, compared to Mars. Today, I might talk about weight, but I'm mostly going to talk about mass. So we need to have somewhat of an understanding between those two. And so this would have the least amount of mass, and this would have the most amount of mass. One investigation that I want us to think about with the objects I brought will help us to start to understand what kinetic energy means. What if we want to have all of these objects move at the same speed. And speed is the rate of motion, how fast or slow an object is moving. So if I want all of these objects to move at the same speed, do I push them with the same force? Do I use the same amount of energy to get them moving? So let's think about that. Would I give this light object a soft push or a hard push? Would I use a lot of force or a little force to get this moving at the same speed that I would want my heaviest object to move? Would I use a soft push or a hard push to get my 8-pound exercise ball to move at the same speed as my lightest? What do you predict? What do you think is going to happen before I tried this? And I'm not going to be able to try this, so we're going to talk this investigation through. So, a light object, would you give it a soft push or a hard push to get it to move at the same speed as the heavy object? I would give this a softer push, a soft push to get this moving at the same rate that I would push all of my other objects. So not too much force for this one. But as I kept moving and rolling each of my objects, pushing each one using force, by the time I got to this one, I would need to give a hard push, more force. Why do you think I would need less of a push with the wiffle ball, and then I would have to keep increasing my push or my force until I got to the heaviest? This has a lot less mass than this. So how much energy would we need to stop these? They're all rolling at the same speed. I give them different pushes. So I gave this a soft push. So I would need less energy to stop this because it has less mass. And as I kept going, when I got to my heaviest object, it has the most mass. I would need the most amount of energy to stop it from moving. So this would have the least amount of kinetic energy in motion, and then the kinetic energy would keep increasing until I got to my heaviest object, the one that had the most mass. Does that make sense? So the heavier or the more mass the object, the more kinetic energy. And you could think of that, how much energy would it take for you to stop these objects from rolling? Another investigation we can do to start thinking about kinetic energy is if we took two objects that had similar mass. So I'm going to test this. My tennis ball and my exercise ball. I think of all the objects I brought today, these two may be the closest in mass. So they have similar mass. Maybe not exactly the same amount of mass, but I feel that they're the closest. So now I have the same amount of mass, but I'm going to roll one slower and one faster. Which one do you think has the most kinetic energy? The slow rolling object or the fast rolling object? The faster the object is moving, the more kinetic energy it's going to have. Think about the energy you would need to stop the object. If this tennis ball is going at you really fast, are you going to need a lot of energy, a hard push to stop it, or a soft push to stop it? If this ball is rolling very slowly, are you going to need a soft push to stop it or a hard push to stop it? So the more mass an object has, the more kinetic energy it has. The faster the object is moving, the more kinetic energy it has also. When it comes to potential energy, which do you think would have more potential energy? Something that's really high up, maybe a heavy rock, or maybe there are two cars that are way up high. And if we were to drop that heavy rock, if I was to drop this tennis ball, would it take a lot of energy to slow it down? What if it was very close to the ground? Would it take less energy to stop it? So the greater the height of an object, then the more potential energy it's going to have. And also the more mass an object has. A big giant rock on a hill versus a tiny little pebble on a hill. Which do you think has more potential energy? That big rock is going to have a lot more potential energy than the tiny little pebble. So I want you to think about evidence. How do we collect information to make sense of how speed and energy are related? And energy has lots of different types, and we didn't even talk about some of them. And it has two forms, energy in motion, kinetic energy, and energy that's stored. And we need to talk about mass, how much of an object there is, and we need to talk about speed, how fast that object is moving when we're talking about the forms of energy. At the end here, I want you to think about maybe creating a model of some test or investigation that you might try at home to explain the difference between kinetic energy and potential energy. When we're creating models, which are a representation of what we're trying to explain or how something works, make sure to include key vocabulary: energy, speed, motion, force, mass. We can also include drawings or images and symbols. And here are some examples of symbols. If the object is not moving, we don't put a line next to it. But maybe if it's starting to move slowly, one line. If it's starting to gain speed and move faster, we can show it with 2 lines. And then if it's moving very quickly, we can show it with 3 lines. We can also use forward, backwards, up, down, give it some direction, even a circular motion. And make sure you also include an explanation. Use complete sentences to explain what's happening. The other fun thing that I want to leave with you is a game. And this is something that I would do as a kid. I want you to test different objects that roll with different masses at different speeds, and then create a bowling game at your house. I used to create bowling games all the time when I was a kid. So here are some objects I pulled out of my recycling, and I want to share them with you to give you some ideas. I have some cans. I have some plastic bottles. This had dish soap in it. This one had fabric softener. So collect different items in your home to create your own bowling alley. Now, I did some research, and a bowling pin weighs about 3 pounds. What does that feel like? Well, I encourage you to look in your bathroom, because shampoo bottles and other types of bottles have labels, and the labels will tell you the weight. You can also look for things in your kitchen and start to compare different weights and pick them up and get a good feel if it's completely full, or if you have an empty one, completely fill it. And then you can get a sense of how much something weighs. And you can also look in cleaning supplies, but be careful, ask a grown-up if you can check out the cleaning supplies. You can also fill your empty objects with rocks or sand so that they will stay in place. Remember, we want some weight in there. We want them to be a little heavy. And then try your different objects, roll them at different speeds, different masses, and create your own bowling game. So thanks for joining me today, and until next time, I hope you have a great day.
All right. Good morning and happy Thursday, everyone who's at home at APS today. We are welcoming our 4th and 5th grade mathematicians. It's time for math. Yay! So this is Miss Carnes here with you, and I have a bunch of my other teacher friends with me, and we want to keep you thinking about math and number sense and problem solving. So this morning, I'm going to start off with a routine we tried last time we were together, if you were with us. So I'm going to show you a visual model, or a picture, that shows an amount, a fractional amount. But guess what? It only shows part. The rest is hidden. So we are going to use that visual model, talk about how many there are in all, how many we can see, and then we're going to try to figure out how many are hiding. So we'll be solving a special kind of addition problem called a missing add-end problem today. What we're going to do a little differently today from last time, if you were with us, is we're going to connect some notation to our problem solving and thinking so we can see especially what our thinking might look like on a number line. So I hope you're ready. And this might help you a little later. I think you're going to be placing some fractions on number lines a little later in today's lesson. So one thing you need to know about this routine is whatever units you see are the same kinds of units that are covered. So let's start talking about our first model here. So the total represented on this poster, although you can't see them all, is 5. Okay? So let's talk about what we can see. I see 2 wholes plus another third. Okay? So we want to figure out then how many more we need to make 5. So our missing add-end problem will look like this. 2 1/3 plus something, we don't know yet, will equal 5. So let's take a look at what we have and think about that for just a moment. Think about what you see. I'm going to go ahead and get our number line started. This is a special kind of number line called an empty number line. So that means all the numbers aren't filled in to start. We are going to add numbers to the number line as we problem solve to show our thinking. So I'm going to start thinking about this problem by starting with 2 1/3, what we can see on our poster. And I'm going to put 2 1/3 right about here on my empty number line. So let me ask you, 2 1/3 is here. Where would 2 be on here? I'm not going to add it, but let's just kind of think about it. So 2 1/3 is here. So 2 would be somewhere right over here, right? Not a full jump of 1 backward because 1/3 is smaller. It's less than 1. So we know 2 would be here, right? And maybe just for our reference too, we could think about where would 3 be? Probably somewhere over here, okay? So let's go ahead and start adding on. So starting with 2 1/3, I think I want to go ahead and make some jumps to get to the next whole number. So since I know everything is going to be wholes or thirds, I'm going to add another third. See where I end up. So here's a jump of plus 1/3. So 2 1/3 and 1/3 more gets me to 2 2/3, exactly. Let's add another jump of 1/3. So now 2 1/3, 2 2/3. One more third is 2 3/3. What do we know about that? 3/3. 3/3 equals 1 whole, right? We can see it right here. 3/3 equals 1 whole. So when I get to 2 3/3, I've added another whole. So I'm at 3. And remember, we're trying to get to what? 5. So this is a pretty easy jump. I'm just going to make a big old jump of 2 whole numbers. 3 and a jump of 2 is going to get me to 5. So let's think about what we added on. We added on 1/3 and 1/3, 2/3, plus 2 more. So we've added 2 2/3. So should be then that 2 1/3, we will write this in a different color. 2 1/3 plus 2 2/3 should get us to 5. But I'm a little unsure, so I want to check it. I want to check it a different way. And it also might match another way of thinking about this. So let's create another number sentence down here. I'll use my blue to kind of separate our sections. So 2 1/3 plus 2 2/3. We can also figure this out by kind of splitting apart our wholes and our fractions. So let's go ahead and do that. So first, I'm going to work with my whole numbers, my 2's. So 2 plus 2 is going to give me 4 wholes, right? Now I want to work with my fractions. So I'm going to put together 1/3 and 2/3. So 1/3 and 2/3 gets me again 3/3. What do we know about 3/3? It equals 1 whole. So our problem here is actually then 4 plus 1, and that makes our target number of 5 we were able to solve. And I had another problem for you today, but I think that we are actually going to run out of time. So maybe we can save it for another day. Hopefully this got you thinking a little bit about putting together fractions, how we can show what we know about fractions and number sense about them using the number line, thinking about jumping to whole numbers. And we also had another way of putting our fractions together by working with our whole numbers first, then our fractions, and putting them all together. So thank you all for working with fractions with me again today, and I'm going to turn it over to Miss Gaudette.
All right, hello everyone. Again, my name is Mrs. Gaudette, and we're going to be working on some problem solving. So let's move this out of the way so that we can see our problem. If you haven't had a chance to do so, go ahead and pause me, download the task, or get out a sheet of paper and something to write with so we can work together. Last time we worked on some buttons problem. And this time I'm going to switch it up, since we were working on some patterning, to looking at some fractions. With that, let's go ahead and let's look at our task. Reminder, I do an abbreviated, I adapt the marking up the text, thinking about what are the quantities that I need to be thinking about and what is it asking me to do. Because always we need to think about what are we asked to do versus what I want to do. Because there's a lot of times that in my mind I come up with what I think I'm supposed to do, and I just run with it, and oops, I made a little boo-boo there. So let's always make sure we know what we're being asked to do. So you notice I have a number line, 0 to 1. Then our first question says, mark the position of the two fractions 2/3 and 2/5 on the number line. Okay, let me think about this. I'm going to start with 2/3. So we know we have to do 2/3. We know we have to do 2/5, and then what are we being asked to do? Thank you. Yes, we're asked to mark the position. So if I was looking at this 2/3, how could I do this? Because whoever did this to me put a half in the middle and messed me up. Because it's so much easier when it's not there. But then we have to, in our minds, think about where would what the different thirds be. That's always how I look at it. I think about the denominator, and I think, how many pieces do I need of this? So I know I need 1/3. So if I position that, would I get about equal parts? About. So I'm going to go ahead and position my 1/3. And I'm to mark the position of 2/3. So I know I have 1/3, 2/3, 3/3. So I will mark my 2/3. Then I need to mark my 2/5. Oh, this one's a little bit more tricky. So if I was to look at that, using my same thing that I did before, thinking about taking the whole and breaking it up into thirds, I can break it up into fifths. Ooh, but fifths isn't very easy. Can you do it? Good, I'm glad you can. Go ahead and try it out while I try to do it, and let's get those fifths going. 5 different pieces. So how many lines do I make? I make 4 lines, right? Because this very last line is my last to finish it off. So I'm going to go ahead and start with fifths. 1, 2, 3, 4, 5 fifths. It's a little off, but that's okay. So I'm to mark 2 fifths. 1 fifth, 2 fifths. So I'm going to mark 2 fifths on my number line. Have I finished the first question? Yeah. We were asked to mark the position, so we have. So let's go ahead and move on to the next one. We are to explain how you decided where to place 2/3 and 2 fifths on the number line. So again, we circle our quantities. And I'm going to underline what I was asked to do. I'm going to explain how. So explain how, and I'm going to under the number line because the number line is a very important piece of this. So I'm going to take this, and let's talk about explaining. Okay. So I'm on number 2. Again, it's always good to label what number you are on your paper. So it says explain how you decided. So what did we do to get that 2/3 and that 2 fifths on there? What did we do? Great, thank you for calling that out. I appreciate it. So we pretty much decided that we took the denominator. So take the denominator. Sorry guys, that's how I have to spell out denominator. It takes a little bit on me to spell it out. Take the denominator to decide the number of spaces on the number line. So for example, if I had a 3 for the denominator, then I knew I had 3 spaces. If I had 5 for the denominator, I had 5 spaces. So take the denominator to decide the number of spaces, and then I had to mark that amount on the number line. So for me, I took a 3, and a 5. So that helps me out that I had 3 and 5 spaces. Okay. Did I answer number 2? Let me see. Explain how you decided where to place 2/3 and 2 fifths on the number line. Did I finalize it? Did I answer that? No, I didn't. Right? I sat up here and I just talked about the number of spaces. What did we forget? Thank you. I appreciate your input. So now from there, I found where 2/3 was and where the 2 fifths was. Meaning I counted off 2, 2. Okay. You may have said it differently, and that's okay. Remember, you have your own thinking here of how you did it. This is how I did it. So be honest. Whatever the way you did it, put it on there, how you solved that. So let's look at the next question. Question 3 says, which of the 2 fractions, 2/3 or 2 fifths, is nearer to a half? And explain. All right. So let's circle our quantities. 2/3 and 2 fifths. You notice it's on there over and over again. So 2/3 and 2 fifths must be important to us. But what's different on this one? It's the half, right? So we need to do a half. And then we have to say which of it is nearer and then explain. You notice we have to do 2 things here. We have to talk about which is near and then how do we know? So let's go ahead and start that. So let me get a new sheet of paper since I love to write very big. So based upon our fraction, what do you think will be nearer? We have the 2/5 here. Here's the 1/2, and then we have the 2/3 over here. I hear you guys shouting at me. Thank you for your input. So again, let's label it. And you guys all told me it was 2/3. You guys are already yelling at me. It was 2/5. So 2/5 is nearer to 1/2. Now comes the hard part. We have to explain. But you know what? I'm up for the challenge. Are you? Good. So let's go ahead and let's look at that. We could say, well, the position on the number line is 2/5 is nearer to 1/2. We could. But remember, we rough estimated about those positions. So let's get a little bit mathy on ourselves. Okay? I like that. I'm glad you guys are open for that. So we're going to go ahead and let's look at this. I know I have 2/5, and I know I have 1/2. What could I do with the fractions to help me out? All right, very good. Equivalent fractions. I have a 5 as a denominator and a 2 as a denominator. What is our common denominator? Well, I'm going to start with 5. Can 2 go into 5 evenly? No. All right, my next multiple is 10. Can 2 go into 10 evenly? Yep, you got it. So let's use 10 as our common denominator. So if I was to get from 2 to 10, what am I going to multiply 2 by? 5. So I'm going to multiply 2 by 5. So 2 times 5 is 10. 1 times 5 is 5. And then do the same. How did we get from 5 to 10? Times 2. So I'm going to do the same over here. 2 times 2 is 4. All right, well, we know that this is only 1/10 away. But if I was to go to 2/3, we could also add in 2/3. So what I'd like you to do now is I would like you to go ahead and finish this off and see if you can get to the thirds, the halves, and the fifths, and find a common denominator to prove that this is much closer than this. All right, so I'm going to leave you with that, but I am going to move you on to Miss Obenchain so that you guys can work on a read aloud. Hopefully she has a great book for you again today.
I do. Hello, mathematicians. I'm Miss Obenchain. Before we get to our book, Miss Karnas asked me to pull the sheets off of her problem that you guys were working on because she wanted you to see the visual that went along with what you figured out. And I think you figured out that it should have been 2 2/3 that was under the screen, and that is what was covered up with the splat. Okay, the book that we're going to read today, before I tell you what it is, actually I'm going to take these down also. I have a question to ask you. Do you think that 1 million, 1 billion, or 1 trillion is the biggest number? We're going to kind of shift gears from fractions now, and we're going to think about whole numbers, but really large whole numbers. So think about that. 1 million, 1 billion, or 1 trillion. Let's read our book today and see if that helps us decide. So today's book is called How Much is a Million by David M. Schwartz. Pictures are by Stephen Kellogg, and it was published by Scholastic. So this is a pretty quick read, so we'll just read through it, and you can look at the pictures. If 1 million kids climbed onto one another's shoulders, they would be taller than the tallest building, higher than the highest mountain, and farther up than airplanes can fly. That's pretty big. If I wanted to count from 1 to 1 million, it would take you about 23 days. Can you believe that? If a goldfish bowl were big enough for 1 million goldfish, it would be large enough to hold a whale. Presto, 100 stars. If this book had 1 million tiny stars, they would fill 70 pages. So climb aboard. These pages have tons and tons of really tiny stars that you might not be able to see, but there's lots of stars on here. So let's see. 1, 2, 3, 4, 5, 6, 7 pages so far filled with stars. And the balloon is saying, there you have 100,000 stars. If we take a 7-page journey 10 times, we'll pass 1 million stars. And the passengers are saying, let's do that later. I'm hungry. I'm thirsty. All right, what about 1 billion? How big is 1 billion? If 1 billion kids made a human tower, they would stand up past the moon. If you sat down to count from 1 to 1 billion, you would be counting for 95 years. If you found a goldfish bowl large enough to hold 1 billion goldfish, it would be as big as a stadium. If this book had 1 billion tiny stars, its pages, spread side by side, would stretch almost 10 miles. How tremendous is 1 trillion then? If 1 trillion kids stood on top of each other, they would reach way, way, way beyond the moon. Beyond Mars and Jupiter too, and almost as far as Saturn's rings. If you wanted to count from 1 to 1 trillion, it would take you almost 200,000 years. And if you put 1 trillion goldfish in a goldfish bowl, the bowl would be as big as a city harbor. That's bigger than any of the lakes that we have here in New Mexico. If you put 1 trillion of our stars onto a gigantic roll of paper, it would stretch all the way from New York to New Zealand. That's like halfway around the world. Back in the back, they've got some interesting things that we're going to talk about in a minute. But what would you decide? Do you think 1 million is bigger, 1 billion, or 1 trillion? Let's write the numbers and see what we think. So if we start with 1,000, 1 million is 1,000 thousands. So we need to add 3 more zeros. 1 billion is 1,000 millions. So we need to add 3 more zeros. And 1 trillion is 1,000 billions. Wow, my commas got a little big there. So we need a whole nother set of zeros. So I think that we could probably say that the trillion is the biggest number, right? The interesting thing about this book is that in the back, they actually figured out these comparisons that they gave you with real calculations. They figured out that the average elementary school student is about 4 foot 8 inches. And so they figured since they're standing on each other's shoulders, you take off maybe about 8 inches. So they multiplied 4 feet times 1 million kids, and they got 757 miles. So if you compare that to Mount Everest, which is the largest mountain in our world, that only goes about 5.5 miles tall. If you compare that to the clouds that float highest up in the sky, they're usually at about 8.5 miles up. And airplanes usually only go about 16 miles up. So 757 miles is pretty big for 1 million kids. With the time it would take you to count these numbers, they gave you about 2 seconds to say each number. So because when you're saying big numbers like 69,999, it might take you a little longer. So 2 million seconds to say a million numbers, which is 33,333 minutes, which makes 555 and a half hours, which is where they got the 23 days. So the interesting thing is if you see this book and you get a chance to see it, in the back they explain how they came up with all of these comparisons. The last thing that we're going to talk about is some comparisons that you could do at home. And so there is an activity called Would You Rather. There's a website called wouldyourathermath.com. And we've linked that for you on the website, so you could go. I have some examples, or you could go to the website. But you could think about this. Would you rather have a stack of quarters from the floor to the top of your head, or $225? Well, I thought right off the bat, maybe I would rather have $225. But then I started thinking about it. And so I got out 4 quarters, which I have in my pocket, and I put them up to a ruler, and I realized, well, 4 quarters was about 1/4 of an inch. So I could get 16 quarters in an inch, which was also $4. Then if I think about how tall I am, 5'4". So 60 inches and another 4 inches, so 64 inches times $4 actually ends up getting me about $256. I'd be better off taking the stack of quarters. So what you need to think about is, what would be good for you? How tall are you? How tall is like your mom or your dad? What would be a better choice for them? And you can figure that out just by knowing how many inches tall you are and knowing that it's about $4 in an inch. You could also go to their website or our website and try some of those other Would You Rather conversations. All right, we're going to wrap that up, and Miss Sears is going to come out here and do a game with us.
I think you're going to stay with me, right?
I am.
So the game that we're going to play is actually called 50 more or less multiplication. So the first thing that you're going to need, and you're going to need this at home, is probably a deck of cards. I've got one, and Miss Obenshain also has one. And what we're going to do is we're going to use our separate decks, but you could also just use one deck if you needed to. One thing before you go ahead and use the deck, you're going to need to remove the kings, okay? Because each of the different cards are going to have different values. Your aces are going to be worth a 1. All of your number cards are worth that given number. And then your jacks are worth 11. And your queens are going to be worth 12. So we're going to be doing possibly some multi-digit multiplication that fits right in with what you should be doing at this time. All right, so let me kind of explain the game. So the first thing we need to do is we need to decide who's more and who's less. And so what I thought, I've already shuffled the decks. What I thought we could do is we could go ahead and flip our first card over and see who has the bigger number. Whoever has the bigger number is going to get to have that choice.
Okay.
All right, you ready?
Ready.
What? Jack.
I got an 8.
All right, so do you remember how much the jack was worth? 11, correct. All right, so I'm going to say less. I'm going to play the odds because I feel like there's going to be less face cards than there are going to be regular numbers 2 through 9. That's just my feeling.
It's numbers that the answer is less than 50, right?
Exactly, yes. So what we're going to do is when we each flip a card, I'm going to flip a card, she's going to flip a card, we have to multiply those numbers together, okay? When we multiply those numbers together, that answer, that solution has to be, or the product of those two numbers has to be either less than 50 for me to get the cards or more than 50 for Miss Obenshain to get the cards. The person who has the most cards at the end of the game or who runs out, the one who has the most cards is obviously going to be the winner. So we're going to play a couple of rounds with you. And if I need to, I'm going to actually try and maybe solve some of these so that we can kind of see maybe how I figured them out. Because not always could we memorize these facts, especially when we get into that multi-digit multiplication. Mm-hmm. We may need to use a different strategy to help us figure that out. All right. So are you guys ready? All right, cool. All right, here's our cards. My card is a 9.
Mine is a 3.
Okay, so I have to do 9 times 3. All right, so 9 times 3, that's one of those facts that I probably memorized. But if I'm thinking about it, I could kind of distribute that 9 a little bit. I know that 9 is 4 more than 5, and I know my 5s. So I know 5, 10, 15, and then I'd have to do 4 more 5s. So 20, 25. Well, no, I'm not doing 5s.
You're doing 3s.
I'm doing 3s. I better start counting in the right multiple, right?
You know what I thought about? Was actually 9 is really close to a 10. So if I multiply 3 times 10, I would get 30, and then I just have 1 extra 3 that I'd have to take away.
So 30, I'm going to use your strategy. I think that's a much better strategy. 30 minus that 3 is going to give me 27. So is that more or less? It's less than 50. Give it over. Give it over.
I'll just make a pile for you of the cards that you want, and I'll make a pile of the cards
All
that I
right.
want.
You ready to go? Here, let's do the next one.
Okay.
I have a 7.
I got a 2. I think the Sears strategy might have been good about picking the lower number, right? Because 2 times 7, that's like a double, right? 7 plus 7 is 14. So if you know your doubles, you could use that. So 14 is less than 50, right? So she wins another set of cards.
Now, where am I going to put the cards if you win? Do you want me to put them in the middle here?
We can just do a stack.
Okay, do a different stack. Sounds like a plan. All right, my number is 9.
I have an ace. That's a 1. Right?
Okay, so 9 times 1. Anything, remember we know this about our multiplicative identity property. Anything times 1 is going to be that same number. So 9 times 1 is 9. Is it still less than 50? Yep, it's mine. Hand it over.
Wins again. I'm
Maybe
not
we
doing
can drop
very well.
the number a little bit. I don't know. Maybe we might want to say drop a number a little bit smaller. We could do that. All right, I have a 6.
Me too.
Oh, this is one of those square numbers.
It
I
is.
remember that. Remember?
We played a game last time on Tuesday, right, where we were using square numbers. If we were charting the area of this, it would be a square shape.
Yep. All right, well, it's your turn.
Oh, it's my turn. Okay, well, I'm going to use your strategy about, if I didn't know 6 times 6 right away as a fact, I would use Miss Sears' strategy about using my 5s. And 6 times 5 is 30, and so 1 more 6 would be 36.
Perfect.
Still under 50, though.
Still under 50. I think maybe we should have done 30 or less, maybe.
Right.
Maybe
the game, we could do how many more or less than 30.
We haven't had any face cards. I mean, and I did shuffle these pretty good. But remember, we only have, in a deck of 52, when we remove those kings, we'd only have 4 of the jacks and 4 of the queens. So that's only like 8 cards in this whole pile. So
True. I would only have won one of the hands, though, only if we had played how many more than 30?
All right. Let's do one more round each,
Okay.
and I think then we can kind of talk about what we've done today.
See if I can win one.
Let's hopefully. I have a 6.
I have an 8.
Ooh.
Close.
Very close. Yes. Oh, because remember we're talking about 6 times 8. I know that's 48. I used to know a rhyme about that. So that's how I know. But she was very close, very, very close that time. She was only 2 off of the 50. So she very well could have won that.
So you could play this same game and just change it to not more or less than 50, but more or less than 30.
Maybe 40.
It might come out a little bit more even. But really, I would have only won a couple of hands if we had it at 30.
Yeah.
So.
All right. Well, so do we want to kind of talk about what we've done today? I mean, we can recap a little bit of what was happening here. Remember Miss Carnes had come up here. We were really comparing a lot of different quantities.
Yes.
Quantities of different magnitudes. We'd have very, very small pieces of numbers, which were fractions, and we had very, very large numbers that Miss Obenchain was talking about when we were talking about money. So we've had a lot of different ideas today about how we were comparing quantities, and the final thing that we did is we kind of compared quantities based on kind of a benchmark number. When we played cards, we were looking to find out if a number that we multiplied together with our card deck would make it closer to this benchmark number, this 50 or 30 or whatever else we could try to do. So I think we've done a lot about comparing quantities today, and it's been very interesting that we've had some fun with our mathematicians at home, and we've given you some ideas that you can definitely work on. So we would like to go ahead and wrap up this session for you and want to thank you for joining us at home with APS. And we hope you have a great day. And thanks so much, mathematicians.
Bye, mathematicians.
Bye-bye.